Okay, good morning, everyone. Welcome to our today's talk of Monash Software Systems and Cybersecurity seminars. Today, we are very happy to welcome Dr. Tarik Moataz, who is a principal research scientist in the cryptography research group at MongoDB. Prior to this, he co-founded and was chief technology officer at Aroki Systems, which was acquired by MongoDB earlier. He was also visiting scientist and postdoctoral researcher at Brown University in the Encrypted Systems Lab. His research is in the area of cryptography and computer security with a focus on encrypted search, which is exactly the topic of today. So thank you, Tarik. I'll stop sharing and you can go ahead.
Yeah. Let me share my screen. Share screen. Your screen sharing is paused. Let me see if I can resume it. Yep. I can't resume the screen sharing, so it worked earlier.
Okay, we can give it a try.
Let me try again. How about now?
Yeah. Yeah, all good now.
Yeah, that's great.
Thank you.
Thanks, Mohammed, for the introduction, and thanks for the invitation. I'm really happy to speak today at Monash seminar. So as Mohammed mentioned, today's talk is about encrypted search. So let's get started. So what is encrypted search? So encrypted search is a research area that focuses on the design, analysis, and implementation of cryptographic protocols that allow users to query their encrypted data privately and efficiently. So, and these cryptographic protocols, we often call them encrypted search algorithms, which at the high level, they work in the following settings. So there is a trusted client and trusted server, where the client holds some data. The data can be a database, it can be like a list of documents and files, it can be like some unstructured data. And the goal is to outsource it and be able to search and update it. So how it works, again, at a high level, is that the client will encrypt the data and outsource it to the untrusted server, and the client will usually keep some secret key, and the protocol or the encrypted search algorithm will allow the trusted client to perform search, updates, and so on and so forth. So this is at a high level what we mean by encrypted search algorithms, or ESA for short. So encrypted search algorithms can be designed using various cryptographic primitives. We can instantiate them or design schemes based on FHE, based on property preserving encryption, based on structured encryption, oblivious RAM, functional encryption, and so on and so forth. So there are different ways how we can design encrypted search algorithms, and they will behave differently in terms of efficiency, in terms of leakage, in terms of functionality, and so on. So what do we mean exactly by encrypted search algorithms? So ESAs, there are different high-level applications that you can think of. Like one of them is, for example, encrypted relational databases, encrypted non-relational databases, searchable symmetric encryption, where you want, for example, to encrypt a document collection, encrypted search engines, encrypted blockchain databases. So there are all of these possible applications of encrypted search algorithms, and underneath, they can use different cryptographic primitives, or a mix of these primitives, not necessarily one of them. So encrypted search algorithm made it to real-world deployment, and one of the first real-world deployment was based on PPE, and there were two designs, actually three designs, with one just recently being available. So one in 2015, it was Microsoft SQL Server, where the product was called Always Encrypted. So it was in 2015, and it used PPE, deterministic encryption, in order to design an encrypted relational database. Similarly, like there was like another product by MongoDB called client side field level encryption in 2019, where basically it provided the design for an encrypted non-relational database. And then just this year, Amazon had a new product called the document database encryption. I believe it's based on DynamoDB, which is also based on PPE. So this is based on one primitive. There was also like one product by MongoDB as well based on another primitive based on structured encryption, which would be like actually the focus of this work, of this talk, where we, our group designed an encrypted non-relational database based on structured encryption. And it was released this year. Okay. So there have been quite a few real-world deployments of encrypted search algorithms, and so through this slide is quite interesting. When I was working on the talk, I wanted just to make this a little bit clearer. So in the same kind of vibe, like encryption doesn't equate TLS. Like in the sense, yes, we use encryption to design TLS and a bunch of other cryptographic primitives. It is also important not to confuse structured encryption with searchable symmetric encryption, or to confuse property preserving encryption with searchable symmetric encryption. So we can actually use STE to build an SSC, but it's not equal. And this is really important because when we do analyze efficiency and security, we need to differentiate also like these primitives. So usually when we talk about, for example, efficiency of SCE or security of SCE, it doesn't necessarily translate to SSC automatically. And there have been actually a few of confusion in the area the last few years. I just wanted to make this clarification, which is important actually also for better understanding this talk. So as I said, the focus here will be on SCE, and the reason why actually I personally work on SCE specifically is that it provides this very nice trade-off between security and efficiency, in the sense that we can design efficient protocol that can potentially be deployed, as we have seen earlier in the previous slide, which is the case for MongoDB, but also it provides this very interesting tunable leakage profile in some cases, where you can tune it depending on the efficiency and the trade-offs that you have. You can tune it as you wish. So it has this very nice flexibility, and it kind of sits at the middle. So what is STE? So this is a cryptographic primitive that it was introduced by Chase and Camara in 2010. It was introduced as a generalization actually of index-based SSC, and it focused on how to design data structure encryption schemes in such a way that the data structure is encrypted, but also can be able to be queried privately and efficiently. So imagine the following setting. So this is basically the syntax of SCE. So a client has a data structure. The data structure can be really anything. It can be an array, it can be a dictionary, it can be a multi-map, and so on and so forth. And the first thing that the client will do is that it will call a setup algorithm. So the setup will take as input a security parameter and this data structure. And it will output an encrypted data structure and a key. So the key will be stored at the client on the trusted boundaries, and it will never leave the client. And the encrypted data structure will be sent to the server. And then whenever the client wants to query, there is this token algorithm. So I'm describing the syntax of SCE in a non-interactive way. So there is this token algorithm that the client will compute, that takes as input the key and the query that the user wants to perform, and it will output a token. We usually call it also a search token, and it will be sent to the server. So the server now it receives this search token, and along with the encrypted data structure that it already stores, it will perform a query algorithm that will output the answer. So there are different variants of SCE. There are variants that are called response hiding, where basically we don't reveal the answer to the server, and it is sent back to the client. There are also variants where actually you reveal the answer to the server. So I'm not getting into these details here in the talk. So in terms of security, There is this really nice notion that was actually introduced by the work of Kirschmuller, Gray, Kamara, and Ostrovsky in 2006, where they introduced this leakage parameterized security definition, where leakage was for the first time back then introduced to capture what do we leak to a server through the queries or the execution of the protocol, and even during the setup. So usually what we do is we divide this leakage into different parts depending on the algorithm being run. So after setup, there is a leakage which we call the setup leakage, which capture basically what the server learns about the data structure by just looking at the encrypted data structure itself and before any query or update operations. And then we call query leakage basically the information that the server will learn throughout the execution of the query protocol. So here, as I said, the syntax is described here in a non-interactive way, but you can imagine a syntax where it's a two-party way where there might be some interaction and so on and so forth. And we similarly can define an update leakage LU, which captures the leakage that the server will learn through the execution of the updates. And the leakage parameterized security definition is as follows as this. So we say that an SCE scheme is LS, LQ, LU secure if it reveals no information about the structure beyond LS, and it reveals no information about the structures and the queries beyond LQ, and similarly, it reveals no information about the structure and updates beyond LU. So basically, you can view this set of leakages, or we call usually the leakage profile of a scheme, as an upper bound of what the adversary can ever know about the execution of the protocol. And by knowing the leakage profile, I know what security guarantees you probably have, because it describes pretty well what the scheme achieves. So this is something that I didn't really mention clearly so far. So in this talk, I'm considering the adversarial model where the adversary is persistent. So you can think of it as the server. There are different and various adversarial models that they are also as good to study as well, like the snapshot adversary. There are other leakage adversarial models as well. So, but for the purpose of this talk, I'm going to focus on persistent adversaries.
I guess we can ask some background questions here.
Yeah, go ahead.
So the first one is about the data structure that you are talking about here, that the user needs to keep a local copy and send the encrypted one to the server, right? Can you give me some examples about, what is this structure? Is this about the index for keywords that may be used for search, or what is that really is in the application?
Yeah. So actually, like, just one clarification here. I think that this is just a typo in the slide. So the data structure doesn't stay at the client. It should be outsourced. So this is just a mistake on the slide. So the client is very important, and it's a really great question. The client doesn't keep a copy of the data structure at all. So it's a great question. So to answer your second question, we will see later in the talk how what are the types or the interesting data structures that are actually being studied. And just to give you like an idea, and we will dive into it like in a few minutes. Multi-maps, inverted indices are the data structures that they are widely studied, and they constitute actually like the backbone of many high-level primitives like SSC, encrypted relational databases, encrypted non-relational databases. There is a bunch of high-level applications that make use of multi-maps. And I'll get to that later in the.
And also another quick question is about the property. For example, an obvious question here is that whether there is a requirement to guarantee the correctness of the answer in terms of, for example, the completeness and soundness. Is that a part of the properties required by this structured encryption as well?
Yeah. So this is a really good question. So in the security definition of SCE, so it is like in the real ideal world paradigm where we assume that actually it's not clear from the security definition, in the sense that when you read it, you will not see that there are any correctness guarantees in some sense required by SCE. But when you think about it a little bit, it's kind of like encompassed in the security definition as a definition in there, where we would like to have some correctness guarantees. Sometimes in some papers, they explicitly mention it. And we did it like in a few works, like in a work I had with Seni and Olya Ohrimenko, like 2018 on leakage suppression, where we made the decision to clearly state the correctness guarantees of SCE. But yeah, like it depends on the work. Sometimes it's not clearly stated, but usually it is required.
Okay, thank you.
Yeah. Okay, great. Those are great questions. Thank you. So yeah, so we went over the security definition. So let's go back, and this is actually like tied to the question that just has been asked. So as I mentioned, SCE is a crypto primitive to design ESAs, but SCE itself can have various types. There are encrypted arrays, encrypted dictionaries, encrypted multi-maps, range multi-maps, and so on and so forth. And you can really imagine SCE as this big umbrella that basically encompasses all of the type of data structure and show how to encrypt them. We don't have instantiation for all of the data structure. I don't think so. But the main ones that they are really heavily studied are multi-map encryption schemes. Recently, a little bit range multi-map encryption schemes, but definitely multi-maps are the ones that receive most of the attention. So SCE actually, like, let's go back and talk about the history of SCE. It's a long line of research with so many dimensions, and it's branched out in so many ways that I'm going to discuss in a bit. And there are so many works, and this slide doesn't list all of them, and it's not an exhaustive list, but the area has matured, and there are so many great research results, starting from the first work where encrypted search was initially explicitly stated by Song, Wagner, and Tarik in 2000, going through the really nice work by Eugene Go, and going through the CJKO by Kurt Muller et al., and so on and so forth. Just amazing works. And these works, as I said, like, this is not an exhaustive list. Sorry if I'm missing your work. These are, it's a really massive, it's getting to be a massive area. But we can divide these works into three main categories. These work, there is a subset of them that focused on efficiency, another subset that focused more on improving the expressiveness of SCE, and also works that studied security. And we can also dive a little bit deeper, as I said, like during the last 20 or almost 25 years of research, there are various dimensions that started, branching out from the area, and you can view even efficiency as multiple categories. So there are works that focus on designing optimal schemes, and by optimal I mean designing, for example, multi-map encryption schemes that they have optimal get operation or optimal updates time. There are also work that they focus on dynamism, and by dynamism I mean the ability to update the data structure, and this happens to be a highly non-trivial problem. And because there are so many things that you need to account for when you are working on dynamic data structures. There is also another branch about I/O efficiency, which started in 2014 and includes locality and recently page efficiency, to improve actually the efficiency of data structure encryption schemes. And if we move to security, like a non-trivial amount of work, and I'm not by no means listing all of them, there are numerous works that studied leakage from an empirical standpoint. And I'm calling it cryptanalysis of encrypted search, where the idea here is to understand empirically how good or how bad the leakage profile of a specific scheme. Because remember, the security definition of SCE doesn't state how good or bad your leakage profile. It just states this is the leakage profile of your structured encryption scheme. So there is a need, of course, to better understand, okay, how good or bad this leakage. There is also another category that I call security properties, and this include forward privacy or forward security, backward privacy, and various security properties that they were introduced as a really interesting aspect of SCE schemes. Then there was like this very recent branch that was introduced in 2018 that we call leakage suppression. And the idea here is how can we suppress the leakage of an existing scheme without having to reintroduce a new scheme? How can we use existing schemes and suppress their leakage in a careful way? And finally, like this branch really started very recently for SCE. So the work on 2017 and 2019 by Jurado et al. And Wright and Puyo in 2015 are more on PPE. Really, the work on SCE started in 2022, 2023 for leakage quantification. So this is really the high-level overview of the field, like, and with all of its branches. For this talk, of course, we are not going to go over all of these categories. I'm going to focus on a few of them. And the idea is to show you the challenges on how to move from a simple static scheme and how to make it dynamic, how to make it more expressive, while also talking about leakage analysis and leakage suppression. So this is the plan for the remaining part of the talk. So let's start with some background. So I'm going to use dictionaries and multi-maps, especially multi-maps, a lot throughout this talk. So let's define what are these data structures. So dictionaries are data structures that map labels to values. They are really simple structures, and they support in the static setting a get operation, where basically you give it a keyword and it returns, for example, the ID. And here I just made the example where I map keywords to ID, but you can imagine any space, you can map any label to any value. So this is just like a really interesting example because it has been used a lot in the area. Multi-maps are kind of like a generalization of dictionaries, where now every keyword maps to a tuple with variable length. And it's not like a one-to-one value, it's one-to-many, and the many can be variable. And it does also support a get operation, where when you feed it the keyword, it outputs the tuple. And here, for example, like when I feed the get operation, the keyword W3, it will output ID2 and ID4. And you can also define range multi-maps. We are not going to use range multi-maps in this talk, but I thought that it's interesting to show as well, where here the label space is ordered instead of not being ordered, and it supports a range operation. For example, give me all of the IDs between 2 and 4, and it will output whatever the documents are verifying the predicate here. So we are going to use mostly dictionaries and multi-maps, as I said. And we are going to use also some terminology when it comes to leakage. And in encrypted search, there are a few leakage patterns that you hear a lot about. And the two most widely used one are query equality pattern and response identity. So the query equality pattern, QEQ for short, is the leakage basically that reveals if and when the search query is the same. So we usually use the word search pattern to denote this as well. Response identity pattern is it reveals the file identifiers matching the query. For example, when I do a query, it reveals the answer, and we call it sometimes the access pattern as well. There are other patterns that were studied as well in literature, like the co-occurrence pattern, which reveals the identifiers in common between any two keywords, or the response length pattern, which is basically the size of the response. Just a remark here is that if a scheme reveals the response identity pattern, then the co-occurrence pattern and the response length pattern can be just computed based on the response identity pattern, because there is already all the information there. Okay. So, as I said earlier, like I will start with the static EMM to describe how encrypted multi-maps work, and then I will build on it just to showcase all of the challenges. And one of the really simple and elegant construction is due to Cash et al. In 2014. It's called PyBase, and it works as follows. So there is a setup algorithm that takes the multi-map and the security parameter, and it performs the following steps. So the first step is it takes the multi-map and it will chop it into pairs, and it will create a dictionary based on these pairs. So for example, here we have the tuple the keyword W1 mapped to ID1, ID3, and ID4. So what we do is we create 3 entries in the dictionary where the keyword one is mapped into ID1, keyword 2 is mapped into ID3, and so on and so forth. And we do this for all of the keywords. So basically, we flatten the multi-map into just a dictionary, and then we encrypt this dictionary. And there is like this really nice way of doing that, which works as follows. So the first thing we do is we derive keys based on the keyword. So let's say we have keyword W1. So we derive 2 keys, one for PRFs and one for an encryption. And then, based on the number or the size of the tuple, we will have as many tags in the dictionary, as many entries in the tuple itself. So for example, here we know that W1 has 3 entries. So we will have 3 tags. And the tags are computed by just evaluating the PRF on a counter, 1, 2, 3, and using the key for the keyword, the derived key for the keyword. And this is how we build the encrypted dictionary. And for the values or the IDs, we encrypt them using a symmetric encryption scheme using a derived key. And that's it. So it's a really simple scheme that has a very nice setup leakage, and we will see later that the GET operations behave really well. So here I described the GET protocol. It's a little bit different from the syntax that I have described earlier, where we had the token and the query. Here I described the GET protocol as a 2-party protocol for simplicity. And the first step to perform the GET, we will have the client generate these derived keys. So let's say that the client wants to get the tuple for keyword W3. So the first thing that the client will do is that it will generate the 2 derived keys, the key for the PRF and the key for the encryption. And to do that, the client will simply apply the PRF on the keyword W3, concatenated to 1, and for the encryption concatenated to 2. So we have two different keys. And the client will send these 2 keys to the server as the token. So basically, this will constitute our token if we use the previous syntax. So now the server has these 2 keys. So what is it going to do? It will take the first key for the PRF and it will generate the tags. And to generate the tag, it simply evaluates a PRF on a sequence of counters. So the first iteration, it will evaluate the PRF on the derived key K13 on counter 1. It will obtain a tag, and this tag will map, for example, in this case, to some encrypted value. So the server will go and check whether this tag exists in the encrypted dictionary. If it exists, perfect. I will get the encrypted value, and then it will do the second iteration where it will increment the counter to 2, and it will find the tag, and the tag it will find the encrypted value corresponding to this tag. And in this case, it will find 1. And finally, the GET protocol will stop at the server when it will generate a tag for a counter that doesn't exist yet. And this is the case for 3 because there is no encrypted value for counter number 3. So the server knows that this is the last one and it needs to stop. And the final step is, because I'm describing PyBase in a response revealing way, the server has also the ability to decrypt the encrypted values, the encrypted IDs using the derived keys. So here it will output ID2 and ID4, and the GET protocol will end. So this is a really simple GET protocol that gives us non-interaction because the GET protocol we didn't have any interaction between the client and the server. And we will discuss in the next 2 slides about what is the efficiency and the leakage profile of this encrypted multi-map.
Tarik, can I ask a quick question here about the keywords? So previously you mentioned that the data structure does not need to be stored by the clients. I understand that part now. However, it seems that the client still needs to store a list of the predefined keywords. Is that right? Or if that is somehow can be generated on the fly?
Yeah, no, it's a good question. So usually we assume that the keyword space or the label space in general is public. So what we mean is that the client will know the keywords that it needs to search. And it's fine. Like you can imagine in practical scenarios, let's say that you have an inverted index, which is an encrypted multi-map. You encrypt it, you store it in the server. And then you want to search. You don't need to know what are your keywords in the multi-map necessarily. Like you can just search for something. If you find it, great. If you don't find it, you know you don't have it in the multi-map. So you don't need to keep any states, especially in the static setting, which is what I'm describing here. So you don't need to keep track of any state information. The only thing that you really need to keep is the key. So far, we will see when we will get to the dynamic case that we will need some states, and this is really required. But for now, we don't need a state.
Right. And does that mean that there is an interface for the user to kind of generate the keywords from the natural language search?
So natural language search is so here you are talking at the high level application, right? Because you are talking about how to design maybe an encrypted search engine. This doesn't necessarily translate automatically to an encrypted multi-map. Like encrypted multi-map, what it gives you really is exact keyword search or exact label search. Does this label or keyword exist? If yes, give me the tuple that corresponds to my keyword. But in order, for example, to build high-level application like encrypted search engine or encrypted relational databases or whatever, you still need a lot of layers and a lot of other functionalities that maybe an EMM itself cannot give you. So there is like this gap that I was also mentioning. If you remember, like in the slide, that the primitive here doesn't necessarily equate the application. So there is like this layer that needs to be filled in order to reason about, okay, what is an NLP? What is the functionality that you are expecting from an NLP search, and so on and so forth.
Okay, thank you.
Yeah, sounds good.
Tarik, can I also ask a question?
Yeah.
Maybe it will become clear later on, but is there a reason why we started from a multi-map instead of just a dictionary?
So no, it's great. So if I had time, I would have started from a dictionary scheme. But actually, like I would say that
I mean, in the sense that why are we doing like this translation from a multi-map to a dictionary and not just have a dictionary in the first place?
Yeah. I mean, if we had a dictionary in the first place, we won't need the first step of flattening the multi-map, right?
Mm-hmm.
But there are some non-trivial aspects to that step. So I don't think that is as trivial as encrypting the dictionary. You really need to be careful about how to flatten your multi-map in a careful way, so you don't need a state, and you need to be able to do that. Also, to be able to update that. I'm going to touch on this later on. So you really need to have like some contiguous thing happening, so your search and your updates are efficient. But
okay, one more quick question. So when the client does this step number 1, how does the client know like how many counters it needs to use? Like it's using 1 and 2 at the moment. Like why not keep going like 3, 4, 5? How does the client know where to stop if it's not storing the database or multi-map?
Yeah. So you are referring to step number 1?
Yeah.
So
when the client does this FK of W31 and then FK of W32, like how does the client know it should not do FK of W33?
Right. So this might be actually like I have created this confusion by having a tuple of size 2. But actually, let me go over this another time. So the first step is just the derived keys. They are not the counter. Like those are just I'm concatenating to 1 and concatenating to 2 just to create 2 different keys, one for PRF evaluations and one for encryption. So the other evaluation, which is based on the counter, is another PRF evaluation on top of this PRF evaluation on the counters, which the server will do.
Okay, so client always just puts 1 and 2, just to always.
Exactly. Exactly.
I see.
Yeah.
Okay. I thought it depended on the number of IDs.
Yeah.
Okay.
No,
all right.
no.
Yeah, I see.
Yeah, great question.
Yeah, sorry,
Yeah.
I also have a quick question here. So here, this scheme is static, right?
Exactly. Yeah.
If it is dynamic, the client need to know the counter, right, for each keyword.
Exactly. Yeah. Yeah. So we will get into how to make this static scheme dynamic, and we will see indeed that we need to keep the state. Otherwise, like it's not easy to do it in an efficient way. But for now, because the scheme is static, we don't need that, this information. Sounds good?
Yeah.
So
Thank you.
just to make sure, Mohammed, just a question about time. So how much time do I?
I think we have about like 20 minutes.
20 minutes? Okay, sounds good. So let's talk a little bit about the efficiency of this static scheme. So it's great, it's simple, it's really elegant, and it has like some great efficiency profile. So first of all, the setup is really fast. It's big O of n, where n is the size of the multi-map, which is like the best that you can do. And it has a get operation that is optimal in the size of the response. Basically, you do a number of operations that is actually equal to the size of the response in big O. And of course, like if we want to get more concrete, this is not exactly optimal because it depends on the underlying plain text data structure. So for example, if you have a hash table as your plain text data structure, then the get can only have big O of the size of R in expectation, but it can do really bad in the worst case, which is big O of n. If the plain text data structure is instead a tree data structure, then the get has a worst case all the time, which is big O of R time log n. So, and we can go on with different plain text data structure. If you use a cuckoo table, maybe you do a constant worst case, but you introduce a state, and it's not as easy to reason about all of these cases. So I'm not getting into the details of the concrete instantiations. So in terms of leakage, the scheme reveals at setup time the size of the multi-map. Basically, like the server, by just observing the encrypted dictionary and by just counting the number of entries, I know the size of the multi-map, which is capital N. And by the way, when I say the size of a multi-map is the size or the total number of pairs in the dictionary. Or you can think of it as the sum of the length of the tuples. It doesn't reveal what is the response length of each tuple, but just the size, okay? And at get time, the scheme reveals the query equality pattern, QEQ, which is if and when the query is repeated. Remember here, like in the get protocol, whenever I query for keyword W3, I will actually indeed generate the same key 1 tree and key K2 tree. So it won't be randomized in any way. So the server will observe this pattern. The server, as we have seen, it observes the response identity because it sees the identifiers. And as I said earlier, by just knowing the response identity, I know the response length pattern and the co-occurrence pattern. So now that we have discussed the static multi-map, and you can view it as a warm-up in some sense, so we will go over all of the challenges of making this static multi-map expressive, dynamic, and probably time will not permit, so we won't talk about leakage, but we will see, and leakage suppression. So how to build, so I will be focusing on conjunctive EMMs. So conjunction is when you search for a keyword and another keyword. And actually we can build a naive conjunctive encrypted multi-map just based on PyBase, and it works as follows. So the setup is exactly the same. We don't change it. We will have our encrypted dictionary, which is the flattened encrypted entries of the dictionary. And then the GET protocol will change slightly, but in a trivial way. So whenever I search for keyword W1 and keyword W3 in my conjunction, so what I'm going to do is I'm going to run 2 instances of the GET protocol of PyBase. So I will search for keyword W1, and then I will get the response, me being the server. And then I will run another instance of the GET protocol to receive R2. And because the scheme is response revealing, the server has the ability to perform an intersection on the responses, which will result in the output. So this scheme is naive. I'm calling it naive because of 2 main reasons. One is an efficiency reason and one is a leakage reason. So let's get into these. reasons. So from an efficiency standpoint, this naive scheme is really poor in the sense that the get complexity is linear in the sum of the sizes of the response of the individual responses. So if I have a conjunctions that has Q terms, I need to search for each of the terms and then sum their responses. This is my get complexity, which is really bad if you think about it. For example, in this example, where I did a conjunction between W1 and W3, ideally, I need to do just a single lookup, just for the keyword, for the ID4. But instead, what I did is I did 2 operations for W3 and 3 operations for W1. And then after that, I did the intersection. And you can think of an example, for example, when you do a linear search because of this naive behavior. Think of a keyword, 2 keywords that actually partition the multimap in 2 different partitions, in such a way that the intersection is empty. So you can still do n/2 here, n/2, and the intersection is 0. So ideally, you should have big O of constant amount of work. But here you have a linear work. So one valid question to ask is that, can we design a scheme with optimal overhead, which is just big O of the intersection? So remember this question, we will get back to it in a second. From a leakage perspective, this naive scheme leaks for each term in the conjunction. And this is at the individual level. The query equality, the response identity, the response length pattern, and the co-occurrence. And here a valid question to ask as well is, can we design a scheme that has a leakage which is only a function of the response, of the overall response? We don't want these atomic leakages for every single keyword in the conjunction. Can we have something that does better? And the answer to both of these questions, the efficiency and the leakage question, is yes, we can. And you can think of a naive solution that will, at setup time, pre-compute all of the possible conjunctions. Let's say the maximum number of terms in a conjunction is known and it's fixed. Then you can pre-compute all of the possible conjunction, store them in the multimap, and then just encrypt that new multimap. And then you will have a get time that it's optimal because you will have all of the conjunctions pre-computed. And then you will have a leakage, which is really good because you won't leak anything about the individual terms. So I'm not describing this naive way to do that because it's inefficient, especially from a storage standpoint and also from a setup time standpoint, because it can be exponential. So going back to what we know, so the best known conjunctive scheme is called OXC by Cash et al. In 2013. And that scheme introduced the first kind of sublinear and with a non-trivial leakage profile that has a get complexity, which is not ideal, as we discussed about in the previous slide, but it's close, where it's now big O of Q, the size of the conjunction, basically the number of terms in your conjunctions times the minimum size of the response. And the idea here is really nice. Basically, it is based on this observation, where when you have a conjunction with Q terms, you can just go first and search for the term that has the least frequent, that is the least frequent. And by least frequent, I mean the term that has the tuple with the smallest size. And when you do that, you will output first the response, and then you will calculate the final response based on just filtering this response, because it's based on this invariant where the final response is necessarily a subset of this R1. So it's leveraging this nice observation, and it has it builds the OXC scheme. So from a leakage standpoint, OXC is also not reaching this ideal setting where the leakage is only function of the conjunction itself. It reveals individual leakage, especially about this least frequent keyword and plus other stuff that I'm not detailing in this slide. So it's not achieving the ideal word in each. So it's kind of like doing better, but still maybe there is room here to improve. And it has this nice property that it does have a constant storage. So there were also like, I want to mention that there were a lot of subsequent works on conjunctive search, on disjunctive search, on Boolean search, because OXC cannot support Boolean in the more general sense in a sublinear way, and SQL and join search more recently. So there have been like really a bunch of new results when it comes to expressiveness. So now that we are done with expressiveness, and now that you have seen the kind of like the challenges, like that it's not as trivial as you may think of taking an EMM and building more expressive schemes, because there is always this trade-off between efficiency and security. The same trade-off also occur in dynamism, and it's really getting a little bit also trickier here. So again here, like, let's design an encrypted multi-map that it's dynamic, and by dynamic here I mean only supporting put operation. Dynamism is really complicated because you can support puts, you can support deletes, edits, appends. So it comes really with various variations. So here, just for simplicity, I will focus on put operations. So let's walk through a simple design from a static multi-map. So remember, like our PyBase in the static setting, it takes a multi-map and the security parameter, and it outputs a key and an encrypted dictionary, okay? And in the dynamic setting, we make this modification that was actually discussed in the previous questions, where we add a state that the client needs to keep. So now, if you notice, the client is no longer stateless. The client is stateful. And it's a really highly non-trivial question, how to make a client stateless. And there was a result that I had recently with Cine on how to do that under some conditions. So what is the state? What do I mean by a state? In this case, specifically for the PyBase construction, a state is a simple dictionary data structure that maps a keyword to a counter. And the counter here is reflecting the size of the tuple. So here we have keyword W1 that has a tuple of size 3. So you will have keyword W1 map into 3, and you will have keyword W2 map into 1, and finally keyword W3 map into 2. So this is what the state is. And so let's discuss the put. So the get is the same, no changes to the get for now. And let's go over the put. So the put takes as input the key, the state, the keyword that you want to update, and actually the value that you want to update, to add, to put in the multi-map, and the encrypted multi-map from the server side. So the first thing that the client will do is they are going to update the state, because now there is this new keyword and this new ID. So the first thing they are going to do is to update this state. So now keyword W1 map into 3, it will be changed to map into 4, because now I have this new addition. And then I will generate this tag at the client. So I will not let the server generate it. So I will first, you can see here in the slide, there are two PRF evaluations. So the first one is the evaluation to generate the derived key for keyword W1. And then the second evaluation to generate the tag, which is now based on counter number 4. And then we will do the same thing for encryption. Here, there are no counters involved. We just encrypt ID 7. So we will send the tag and the encryption to the server. And the server simply, it's a really simple operation. It will just put the tag and the encrypted value in the dictionary. So this is the put operation of dynamic multi-map. So now we didn't touch on the challenges yet, but let's discuss them. So, and to illustrate the challenges, let's think of the sequence of operations. So imagine that the client performs a get on keyword W1, perform a put keyword W2 with ID 3, performs then a get on keyword 3, and then a put on keyword 1. So in this construction so far, as described, the server will learn at the put time that this put operation is correlated with the first get operation. And why is that? Remember that when we do a get in PyBase, we send these derived keys, right? And the server has the ability to perform another evaluation on various counters, 1, 2, 3, 4, and it doesn't need to stop. It can generate all of them And by doing that, it knows future updates. So whenever there is a future update, the server already knows, it's this tag, it's this other tag. And it knows that it's related to whatever search operation that was occurring the first time. So the server doesn't necessarily know what is this keyword, but it knows that this update, it is correlated to that search or to that GET operation. Okay. So more precisely what we say is that the put leaks the operation equality pattern if a GET operation on the same keyword occurred in the past. And Zhang and Katz at Papamanto in 2016, they show that this leakage can be used to recover the queries in the presence of an active adversary. And active adversary here refers to an adversary who can influence the client to perform a certain behavior, like perform certain updates or GET operations. So this observation actually was actually the trigger of so many results in the area. So the researchers in encrypted search area actually quite focused on forward privacy and later on backward privacy a lot. And what is forward privacy? Forward privacy actually was introduced probably prior to Stefanov, Papamanto, and Chi in 2014. Probably it was introduced in the first time, even not very explicitly by Chang and Minzenmacher in 2005, but it was more explicit in this work, where they say it would be ideal actually to get rid of this correlation between the put operations and the GET operations. And the idea here is, can we design a scheme such that when I do a put, it doesn't reveal that this put is actually related to a previous GET operation? And this notion was formalized by a work by Raphael Boss in 2016, where he showed that such a security property can be described by having the update leakage being bought. And by bot, I mean nothing. You don't leak anything during updates, and other than some public information about the size of the ID, which I'm not accounting for here. Okay, so let's get back. I know that I'm almost close to the end, so I'm going to finish this section and then I will conclude. So let's discuss how can we modify the dynamic multi-map encryption that we have designed a few slides earlier into one that is actually forward private. And the idea is really simple. It's a small slight trick at the GET operation. So now let's say, now I have a state. Remember that the client has this state. So now instead of letting the server compute the tags itself, me as the client, I will compute these tags for the server. So now instead of sending this derived key to the server, the client, do all of the work. And I will have a work that is linear in the counter. And it's still optimal because my answer should be at least equal to that. So it's fine. So what the client will do is it will get the derived key and will evaluate it again on 1, on 2. And here we have keyword W3 mapping to 2. So 2 is fine. And then I will also compute the derived key. Okay. And then I will just send these tags to the server. The server will just go and find the corresponding IDs without having to decrypt, without having to do any additional PRF evaluation. And then it decrypts the encrypted values. Okay, so it's a very slight change to the scheme, but it has this really interesting property where you get rid of this correlation between the puts and the gets. And the idea here is that now the server has no longer access to these derived keys. So it has no longer access to, okay, like this is what's going to happen in the future. So we remove this ability from the server to do that. So this is just a toy example how to make a variant of PyBase forward private. So now let's get back to our sequence. So now we have the sequence. So we no longer leak this correlation with the past. However, this scheme still leaks some other form of correlations. So for example, when I do another get, the get will definitely find this new ID, and it will know that this is something for this keyword. And given the fact that we also leak the query equality, I will know the correlation with the first get. And then I can infer this missing edge between this put and get. And this is not actually part of forward privacy. So forward privacy will not guarantee this type of hiding these types of correlations. And because forward privacy only protects against a subset of possible attacks in the ZKP16 called non-adaptive, but the adaptive it doesn't protect against. So in a work that I had with Amjad, Ghosh, and Sini this year, where we introduced a new notion that actually provide injection security in the sense that it will indeed protect against the first types of correlation, but also the future correlation, where we will actually get rid of these two edges. And you don't know really what this put was about. So it comes with some overhead, but it gives you like the ideal security guarantees against file injection and injection in general. So this is really important just to showcase that forward privacy is limited as a notion and doesn't capture really the entire picture, especially when it comes to injection attacks. It just protects against a subset of it. So not all of them entirely. So given the time, so I will unfortunately skip over the encrypted search analysis and the leakage suppression, and I will conclude. So to conclude, I would like to highlight that encrypted search has really grown tremendously in the last 20-25 years. There are so many fascinating results, and we also have seen, which is really nice, real-world deployments of various encrypted search solutions, and especially more recently based on structured encryption, which is highly non-trivial. So there are new research dimensions in the last few years that they are really interesting and that our group also works on. One interesting aspect that I wanted to discuss about in this talk, but unfortunately I couldn't have the time, which is leakage suppression, which is an area that was introduced in a paper I had with Sini and Olia in 2018, which, as I have said earlier, which gives you this ability to suppress a leakage in a generic way, with some cost, of course. It doesn't come for free. There was also like this very nice area about the theoretical leakage analysis for PPE-based ESAs. There was more recently like a new IO efficiency branch, which is called page efficiency, which is basically saying that all of the locality works, they focus on HDDs, that they are not really no longer the medium of storage in modern architectures, and the focus switched more to SSDs, and they introduced this new notion that captures more SSDs than HDDs, that they call page efficiency. More recently, there was theoretical leakage analysis for SCE, and especially like one of the work that I had with Seni, that is available on ePrint, which is on how to quantify leakage based on a framework we call the Bayesian framework, which is really interesting in the sense that basically what we study is, given a leakage pattern and given some auxiliary information or auxiliary distribution about the data or the queries, and actually some users' query distribution or data distribution, can I quantify how bad this leakage pattern is for these specific distributions? And we come up with this notion of coherence that kind of like measures the strength or the accuracy of the inference. And finally, this is something I mentioned in this talk, which is injection security, which is kind of like a generalization of forward privacy, or a kind of it's looking really at the injection from a graph-based. It's really nice because we introduced also this graph-based leakage representation that shows actually how the correlations are drawn, which is really nice to see how the puts and gets can get correlated. So yeah, so this is all to say that we are not done yet. There is a lot of work, and there are several open questions that remain unanswered. Thank you, everyone.
Thank you very much, Tarik, for your very interesting talk. I see Xingliang has a question, I guess. Go ahead, Xingliang.
Yeah, thanks for the talk. Yeah, so I have some questions. So very interesting talk. So first question probably is, you have a slides. You made a claim that ST is different from SSC. Can you please elaborate a little bit more?
Yeah, so this is so this is really common discussion that we are having the last few months. And so actually SSC was introduced in the beginning, if you remember, like in the paper in 2000 and also in 2006, really as a crypto primitive to encrypt a document collection, like documents, like files, and be able to search them, to search over them, like with exact search. You can have SSC with ranges, you can have SSC with NLP, as it was mentioned in a previous question. So this is what is the primitive SSC. So now what happens is that the most efficient SSC instantiations are based on multi-map encryption schemes or inverted indices. So what happens is that there was at some point this switch, or like this translation, where the focus was more on this encrypted structure or this encrypted inverted index, and there wasn't no longer the focus on the encrypted collection of the document. So this is why you will see that actually most of the work that they are still called on SSC, what they are really are about, they are about an encrypted multi-map. And the documents are actually out of the question entirely. Like it's very rare that you will see an SSC paper about like how to search on how to retrieve the documents or how to encrypt the documents even. So, but really, like, this is not good for so many reasons, because even the notion of forward privacy, when it was introduced in 2014, but it was formalized in 2016, it wasn't really a notion for SSC. It was really about the multi-map encryption scheme, because now if you include documents in the picture, it's no longer clear what you will mean with forward privacy, because it gets really tricky. We will need more time to discuss about that, but it's really important to, I think that there was like at some point like SSC means SCE, but it's really it's a confusion, because SSC can be itself designed in so many ways. I can design an SSC scheme based on a tree-based ORAM, where I can store the documents in an ORAM, and I can store the index with a black box simulation using a RAM encryption scheme. So, and there are other ways, of course, to do that. So this is why I would like to make sure that when I was talking about SCE is really about the data structure, and I'm not talking about the documents at all.
Sure.
And yeah,
thanks. Yeah, maybe another question is probably related to, because right now you are working in MongoDB. So I'm just wondering, I mean, because during the deployment, I mean, the example you've shown is simple, right? Because you only rely on the put and get API, so which is already there, for example, for MongoDB or for Redis. But when you talk about some complicated schemes, like some schemes that you have the forward privacy or some like other advanced security features, normally you need server to do some operations. So which means that the API, those standard API may not be sufficient. So I'm just wondering, what kind of like strategy or what kind of like implementation MongoDB have done to achieve this? They entirely rewrite the database engine, or they just put a middleware or proxy to help the server to do the computation?
No, these are great questions. I wish I had more time to discuss, but so the design of queryable encryption, like it was a 2-year intense engineering crypto team project, and there were so many constraints. And some of them I touched on in one of the talk I have given in last year at Crypto. But there were so many constraints and they were like, just to answer slightly your questions, even though like your question is complex and there are so many layers to it. But the engineering team and us as crypto team, when we did the design, there were some phases where there are some computation that the server needs to do. And together with the engineering team, we made the right decisions into what operations need to be done. So we have this very nice paper that it's not somehow it's not really visible and not very well cited in some sense, which is where we talk about the theory of designing encrypted relational databases, and we talk about something which is really nice, which is what we call emulation. And what we mean by that is that we came up with an idea where if you have a client that can store some data, and if you are okay with interaction, which are two things that if QE cannot support, like there were some of the constraints of the design. We cannot support interaction because it kills efficiency. Clients cannot store states because they can come and go. They can run on Dockers and Kubernetes. They cannot like really have like any states. So it was really one of the constraints of the design. But theoretically, like if we talk from a research standpoint, so we came up with this really nice observation that we take an SCE scheme. Given the right API, you can emulate anything that you have through some interaction with the backend. And we call it emulation, and we show how to emulate like a specific SCE scheme.
Okay.
Good.
Yeah. Probably one last question. So apart from this, those constraints, any specific like experience you want to share, especially some challenges in the deployment? Yeah.
So I think that the main challenges, I would say, that were really a big research questions even for us were how to make sure to have stateless clients,
okay.
Have zero interaction, have decent leakage profile against like adversarial models that we made precise, and have concurrent operations for multiple clients, and where the data is also stored in a distributed setting. So it's a lot of constraints, but this is really like the why it made the design quite complex at the end. But I would like, I mean, from a research standpoint, I would like to highlight all of the questions, the dimensions, and they are mostly about leakage. If you remember in the last slides I have, those are mostly leakage related questions. Yeah. But I think from a design perspective, the constraints that I have mentioned, they were really important from a scalability standpoint. And there were so many new results that we are going probably to share in the future as well.
Okay. Yeah. Thanks for sharing this. Thanks.
Yeah, of course.
Hi.
I can see there are more questions, but maybe for the sake of time, what we can do is, since we are going to have another meeting with people from MongoDB, maybe we can also invite Tarik to join remotely and then share more insights then. We are already kind of over time by 10-15 minutes. Is that okay?
Can I ask a quick one, a very quick one?
All right, maybe one last quick question.
Sorry, yeah. So in the example scheme, so we transform the multi-map to single map, right? So I wonder, is the motivation is to hide the structure of the multi-map? Yeah, because the performance is worse, right?
I think that you have the right intuition in the sense that the idea of the design, so this is just one design of possible various designs, like, and this design, the idea is you want to minimize your setup leakage, right? You don't want to have a leakage more than the size of the multi-map. So you want to do it in such a way that the leakage is just capital N, but you want also to make sure that when you do get operation, you don't end up leaking extra. So you can have like examples, for example, if you are not careful, and this is something that I didn't make explicit, like even the dictionary needs to have some properties like history independence, or otherwise you need to permute the entries before storing them. So I didn't touch on these details. but you need to be really careful about how these pairs even are stored. So even lexicographically, that needs to be broken. That link needs to be broken. So I think that the answer to your question is, it's from security. Efficiency, not really much, because I could store all of them contiguously and then be able to search over them, but I will end up leaking a lot more. So it's really a mix of how to maintain a really good efficiency, and in this case optimal, while having to have a very good leakage profile, especially at setup time.
Thank you.
Yeah.
Yeah, it's clear that there is a lot of interest on this topic with its relation to both cryptography and practical applications. Yeah, thank you very much again, Tarik, for your very interesting talk. And thank you everyone for tuning in. Hope to see you all in the next seminar.
Thanks
you.
everyone.
Bye.
Bye.